Somewhere in the middle of the ocean, beyond radar contact with the nearest coastline, 5,000 people are asleep, or supposed to be, and the ship they live on has not touched land in 63 days. There is no sunrise visible from the berthing decks 3 levels below the waterline. There is no natural cue telling the human body whether it is 2 in the afternoon or 2 in the morning. The ocean provides no reference. The steel provides no reference. The only thing preventing 5,000 circadian systems from collapsing into biological chaos is a schedule, a sleep engineering architecture so precisely designed that it governs when each person closes their eyes, how long they remain horizontal, when they eat, when they exercise, and when they are allowed to exist in silence. And if you think managing your own sleep schedule is difficult, consider what happens when getting it wrong does not mean you feel tired at work, but means a nuclear reactor goes uninspected, a flight deck becomes dangerous, a surgical procedure gets attempted by a technician who has been awake for 19 hours, and 5,000 people living in a sealed steel environment with no ability to call for outside help begin to deteriorate simultaneously. This is not a story about military discipline. This is a story about the engineering of human consciousness at scale, inside a machine that cannot afford to let it fail. The first thing to understand is that an aircraft carrier does not operate in time the way the rest of the world does. Civilian infrastructure assumes the sun. It assumes that grocery stores replenish, that hospitals have rotating staff drawn from a surrounding population, that if something breaks down at 3 in the morning, someone can be called in from home. Every civilian system is parasitic on the broader world in ways so normalized that most people never notice the dependency. An aircraft carrier strips all of that away. There is no broader world to draw from. There is no resupply flight arriving tomorrow morning with fresh personnel. The 5,000 people aboard are the entire civilization, and they must operate every function of that civilization continuously, 24 hours a day, across months of uninterrupted isolation. That constraint, total self-containment with zero external fallback, is the design pressure that produces everything aboard, including the sleep schedule. The schedule does not exist because someone decided it was a good idea. It exists because the physics of human cognition inside a closed system with no natural time cues and no rotating external workforce left no other engineering option. The carrier operates on a system called the watch rotation, but calling it a rotation understates its complexity. It is more accurately a compressed civilization calendar, broken into cycles that do not align with the 24-hour day most humans use as their temporal anchor. The most common structure divides the operational day into watches of varying length, some 4 hours, some 6, staggered across departments so that at no point is any critical station unmanned, but also so that no individual is forced into a permanent night shift that their biology will eventually refuse to sustain. Here is what most people never consider. The human body can tolerate a disrupted sleep schedule for days, perhaps weeks, before cognitive performance begins to degrade in ways the individual cannot self-assess. This is not tiredness that feels like tiredness. This is impaired judgment that feels like normal judgment. A person running on 4 hours of fragmented sleep across a 3-day watch rotation does not feel dangerously impaired. They feel slightly tired, slightly irritable, entirely capable of making decisions. And that subjective feeling is precisely what makes the failure invisible until it manifests as an error. Sleep engineers aboard carriers understand this asymmetry, which is why the schedule is not designed around what personnel can tolerate and report, but around what cognitive science says happens to performance before the person notices anything is wrong. Now picture what the sleeping environment itself imposes on top of this schedule. The berthing areas aboard a carrier are not rooms. They are stacked sleeping racks, bunks arranged in columns of 3, separated from adjacent columns by roughly 18 inches of lateral space, contained in compartments that hold between 30 and 60 people simultaneously at varying stages of their watch cycle. If you lived here, you would be attempting to sleep while your shift neighbor dresses for duty, while someone 2 racks above you sets an alarm, while the ship's ventilation system circulates air at a constant mechanical hum that never pauses and never changes pitch. There is no darkness differentiated from daytime darkness. The lights dim on a controlled cycle, but the compartment is never fully silent, never fully still, never free of the low structural vibration of a ship pushing through open ocean at operational speed. Under these conditions, sleep is not something that happens naturally. It is something that must be engineered into the environment, which is why carrier sleep architecture extends beyond the schedule into the physical and procedural design of the berthing spaces themselves. Quiet hours are enforced not as courtesy, but as operational protocol. The compartment's light cycle is controlled centrally and does not yield to individual preference. The ship's internal communication system, the 1MC, is restricted from non-emergency announcements during designated sleep windows for specific berthing areas, because auditory interruption during the first 90 minutes of sleep, before deep slow-wave cycles begin, resets the entire process and costs the individual hours of restorative function they will not have time to recapture before their next watch. But this creates a new vulnerability. Because the ship operates on staggered watch rotations with different departments cycling on different schedules, the sleep windows of different berthing areas do not overlap uniformly. This means the corridor outside your berthing compartment may carry full-foot traffic during your protected sleep window, because the personnel using that corridor are mid-shift and operating normally. The ship's designers solved part of this through acoustic zoning, routing high-traffic passages away from primary berthing areas, using sound-dampening materials on bulkheads adjacent to sleeping compartments, and segregating maintenance work that generates sustained noise into operational periods that avoid the deepest overlap with the largest number of sleepers. But acoustic zoning on a steel ship has hard physical limits. Steel transmits vibration through its structure regardless of surface treatment. The solution for what acoustic engineering cannot eliminate is pharmacological and behavioral, controlled caffeine timing protocols, scheduled light exposure in common areas calibrated to suppress melatonin during wake cycles and permit it during sleep windows, albeit in behavioral training that conditions personnel to sleep in fragmented environments rather than expecting consolidated rest. This is not adaptation in a casual sense. It is a physiological recalibration program that begins before deployment and continues through it. Here is where civilian logic collapses entirely. Most people assume that sleep deprivation on a military vessel is simply an accepted cost, a sacrifice made for operational necessity, managed through willpower and duty. This assumption misunderstands what sleep deprivation does to the specific functions a carrier requires. The flight deck alone requires dozens of personnel performing tasks with physical and spatial precision, directing aircraft weighing tens of thousands of pounds across a surface where the margin between a correct hand signal and a catastrophic misunderstanding is measured in feet. Reactor departments require technicians capable of reading instrument variations that indicate developing faults before those faults become failures, a task that demands sustained attention and pattern recognition, operating at full neurological capacity. Medical departments must be capable of performing surgery, administering complex pharmaceuticals, and diagnosing conditions without the ability to transfer a patient to a superior facility for weeks. If you were staffing these functions with personnel whose sleep had been allowed to degrade freely, the degradation would not announce itself. The flight deck director would still feel confident. The reactor technician would still believe they were reading the instruments correctly. The surgeon would not feel their hands were less precise. The impairment is subperceptual, which means the only defense against it is structural. A schedule that prevents degradation from occurring rather than detecting it after it has. The escalation point in sleep architecture is what happens when the operational tempo accelerates, when flight operations extend, when the ship moves into a higher readiness posture, when something requires sustained around-the-clock activity from departments that are normally on a managed cycle. This is where the system faces its most acute engineering pressure. The watch rotation is designed for sustainable long-term operation, not peak performance bursts, and the two requirements are in direct tension. Surge operations compress sleep windows. Extended flight schedules pull personnel back to the flight deck before their neurological recovery is complete. The ship's sleep infrastructure does not disappear during these periods. The berthing compartments, the light cycling, the acoustic protocols all continue, but the schedule governing who is in those compartments and for how long compresses against biological minimums. The carrier's aviation medicine department monitors this compression through performance data, through incident reporting, through structured check-ins with department heads, and through the kind of aggregate cognitive testing that can detect population-level degradation before it produces individual failures. The monitoring is not therapeutic, it is predictive. The goal is not to help a tired person feel better. The goal is to identify when a department's collective cognitive reserve has dropped to a threshold where the probability of an undetected error exceeds acceptable operational parameters, and to intervene with mandatory rest periods before that threshold is crossed. And this is where the pressure intensifies, because mandatory rest during surge operations has an operational cost. Every hour a department is stood down for recovery is an hour during which some function is either unmanned, reduced to minimum coverage, or temporarily absorbed by personnel from adjacent departments who are themselves mid-cycle. The ship is not large enough to carry redundant full departments. The 5,000 people aboard represent the total workforce, and that workforce is always allocated across the ship's functions, with margins calculated for sustainable operation, not for absorbing additional load. Forcing rest on one department transfers load to others, which if sustained long enough begins to degrade those departments' sleep cycles, which eventually requires their rest, which transfers load further in a cascade that the ship's operational schedulers must anticipate and interrupt before it propagates. Managing this cascade is the highest order function of the carrier's sleep scheduling apparatus. Not the individual's rest, not the department's rotation, but the systemic interaction of multiple simultaneous cycles across 5,000 people operating in conditions that continuously threaten to push at least some of them below cognitive safety thresholds. If you were here during a period when this cascade was beginning, when you could see in the aggregate data that 3 departments were trending towards sleep debt simultaneously, while flight operations showed no sign of reducing tempo, the decision architecture you would face has no civilian equivalent. You cannot hire temporary workers. You cannot delay operations because your workforce is tired. You cannot call in external support. You can only redistribute the existing 5,000 people across a slightly different schedule configuration, accept increased risk in some areas to preserve safety margins in others, and trust that the engineering of the schedule itself, its built-in recovery windows, its staggered cycling, its physiological monitoring, will hold the system above the threshold until the operational surge passes. The carrier's survival as a functioning civilization depends on that trust being justified, which is why the schedule is not designed by operational commanders optimizing for mission output, but by specialists who understand that the mission itself is a dependent variable, dependent on the sustained cognitive functionality of the people executing it. What the sleep schedule ultimately reveals, when you trace its architecture all the way through, is something larger than scheduling. It reveals the fundamental design philosophy of the carrier as a system, that human biological requirements are not variables to be optimized around, but constants to be engineered into the infrastructure. The ship's designers did not build the berthing compartments and then wonder how to fit sleep into the schedule. They began with the irreducible requirements of human neurological function: minimum consolidated sleep duration, circadian anchor points, acoustic and light environment parameters, caffeine and stimulant timing constraints, and built the entire schedule architecture outward from those constants. Everything else accommodates them: watch lengths, department rotations, maintenance windows, meal timing, exercise periods, the 1MC restriction protocols. All of it traces back to a core biological fact, that the humans running this machine are not machines, and that a carrier which treats them as if they were, will begin to fail in ways that no amount of mechanical engineering can compensate for. The ship is not self-sufficient because it carries enough fuel and food and weapons. It is self-sufficient because it carries a complete theory of human sustainability and has built that theory into every layer of its operational design. The sleep schedule is not a convenience. It is load-bearing infrastructure. What has not been examined here is what happens to that infrastructure when the ship operates under full emissions control, when communication blackout is imposed, when the external monitoring and reporting systems that connect the carrier to fleet medicine and operational oversight go dark, and the ship must sustain its sleep engineering apparatus entirely from internal resources without the ability to consult, escalate, or request guidance from anyone outside the hull. That is a different pressure entirely, and it operates on the same 5,000 people, in the same steel compartments, under conditions that close the last remaining door to the outside world.